Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology, and I'm just talking about how carbon is lost from Arctic soils with permafrost. Okay, so you have a river here, you have a thaw lake, so a thermokarst lake, so there was permafrost here. The permafrost had a lot of water content. It thawed, there was a drop, and you have this lake here, and because the lake doesn't freeze at the very bottom, you have unfrozen ground here, and there's permafrost all in this region, and this is an area of unfrozen ground, italic. And depending on whether or not oxygen is available, if there's oxygen available, the CO2 emitted is much higher, methane much lower. If there's no oxygen, you get mostly methane and less CO2. Here's a pond here, more methane, less CO2. Okay, so this is showing annual tundra emission with high and low emission scenarios. And what you can see is, high emission, area 2.2 million square kilometers. In the Arctic is the blue. This is teragrams of methane per year coming out. So you can see an increase here. Now notice this is a slow linear increase. This is direct measurement. This is low emission scenario here. And you can see this is like linear stuff. So we're not talking about huge class rates coming, releasing methane or, significant uptick. So, the Arctic is warming in a very nonlinear fashion. So why would you expect methane to come out in a linear fashion? But anyway. Let's talk now about the ocean. So this is a bathymetry of the ocean, 0 to 5,000 meters, 0 to 5 kilometers deep. What you can see here is you can see the Lomonosov Ridge coming across here. You can see the ocean basins, the Beaufort Sea Basin here, a very deep basin here. Going over to the Atlantic here, but the key thing is the white areas here. Okay, the white areas here, very shallow water. This is the continental shelf that surrounds the Arctic Ocean. There's lots of carbon in the sediments. There's clathrates in the sediments. So as the Arctic Ocean loses its ice cap and the water warms up, that heat percolates down and it thaws the sediment, and you get methane released as a result. The question is, how quickly is it released? How quickly does it ramp up? But you can see how it's shallow, this vast continental shelf area, very, very shallow water. Okay, so this is some of the processes that release the methane, that oxidize it, that migrate it within the ocean and its sediments. Okay, first of all, you have methane, you have thermogenic methane production. This is a geothermal gradient, 30 degrees Celsius per kilometer. Go down a kilometer in the ground, temperature increases 30 degrees, go down another kilometer, another 30 degrees. Gets warm pretty quickly. Over 100 degrees, about 100 degrees Celsius, the cooking process, you get methane produced here. You get microbial methane production, when the temperature is less than about 60 degrees Celsius. The microbes don't like it when it's too hot in general. You get gas migrating upward. Then what happens is the pressure and temperature are such that you get this water lattice, you get these gas hydrates. Water lattice forms around the methane molecules. Up at the top here, you have anaerobic methane oxidation, which breaks down the methane. You can have a sulfate methane transition zone here. So what happens is so as you're deeper and deeper, you get not much sulfate, and then the sulfate increases as you come up. When you're deeper, you have a lot of methane, starts reacting with the sulfate, there's less and less methane. Okay, so this breaks down a lot of the methane. You have the gas diffusing up. This is the temperature profile here. Okay, so the temperature increases as you go up in the water. So as you can get bubble plumes, lots of bubbles, it can saturate the absorbers and make it up into the atmosphere. This is within the water you have oxygen, you have aerobic methane oxidation, breaking down the methane. Up here you have, this is the thermocline where the temperature rises sharply. Okay, it's cold below, sharp transition to the surface temperature of the ocean. This is a surface mix layer. Okay, the thermocline, it's like the cold water below, warmer water above. And here you get aerobic methane production. You get some production near the sea surface, and you get a flux up into the atmosphere as a result. Okay, so that's the marine thing. This is the structure of a methane hydrate block. Okay, German research ship off Oregon, depth of about 1,200 meters. In the upper meter of the sediment, they pulled this chunk out, and you can see the pock marks where the stuff is starting to thaw and give off methane with an expansion of about 160 times in volume. So here's an image of the gas hydrate distribution. Okay, so here we're on shore. We have the thermokarst lakes. We can get methane produced. Active layer, aerobic oxidation. This is a shallow Arctic shelf. You can get methane bubbling up into the atmosphere. There's a region of pressure and temperature where the gas hydrate is stable. Go down further, it's too warm in the earth. You get thermogenic gas produced. Go up above, okay, you have the permafrost. So as you go down, here's the water depth, 500 meters. Going deeper and deeper, we have the gas hydrate stability zone here, and it breaks down here where you get lots of, this is the upper edge of stability, stable below, unstable above, you get bubbling coming up. You can also get cracks and fractures down deeper, and you can get seeps and so on. So this is, the colors, there's young microbial gas, okay, up near the surface. Older microbial gas is further down. Microbes are breaking down the organic matter. There's gas hydrates, both sourced from microbes and thermogenic, and then the thermogenic gas is below. Okay, this is showing, this is gas released, dissociating gas hydrate. Following, this is modeled from a doubling of carbon dioxide in the atmosphere. But again, it doesn't get the Arctic temperature amplification right. So it says here, due to the slow penetration of heat into ocean sediments, this release will take place over many centuries. Okay, so this is, I'd say this is rather a dubious statement. We know that you can't just model the heat going down into the sediments. There's bubbles coming up, there's gaps, there's fractures, etc. It's not a uniform process spatially, so there's weak points, okay? And it's only as things break down when when the weak points are utilized. So the largest reductions are seen north of Novaya Zemlya, okay? So right here, there's a lot here and so on. So these, all along the continental shelf, there's these clathrates, and these are areas that are thought to be more at risk. So if you're looking in the atmosphere and you're looking at methane concentration maps of the Arctic, you want to focus on these type of regions here to see if those are actually sources, especially as the sea ice is declining. Right now in this region, there's very little sea ice year-round, in fact. So this is an area of risk. Now, what about anthropogenic emissions and projections of methane? Okay, so there's all of these different inventories of past emissions, allowing you to do projections of future emissions. There's emission control, at least talked about. These are some of the factors in emissions. I won't go into this in detail. We'll just have a look at some of the data. But these are some of the models, inventory databases and models of global anthropogenic emissions. So covering different periods, different groups around the world. And what you can see here is this is a breakdown of some of the anthropogenic emissions. So we have livestock, a huge factor. Huge factor. If we all became vegetarians, we could really cut this back. Rice cultivation. Okay, here, agricultural field burning, coal mining, natural gas and oil systems. You bring up oil, the gas pressure drops, methane is released. Combustion fuels, solid waste. Okay, so this is fecal matter decomposing, producing methane. Wastewater, industrial processes, and other. I don't see where that is. It should be on the top. Okay, so that's how the breakdown is in anthropogenic emissions. This is some of the breakdown in terms of tabular form with the different models. Okay, so these are it's going livestock, very huge factor, rice cultivation, solid waste, wastewater, coal mining, natural gas production, gas transmission and distribution. This would be leaks in the transmission system. Oil refinery and production, combustion of fossil fuels produces some, biofuels, agricultural waste burning, forest and grassland burning, industrial processes, agriculture, and so on. Biomass, fossil fuels, okay? So this is all the different models to come up with the best number possible. Take the ensemble. Crude oil, natural gas emissions, venting gas, flaring gas, oil refineries, unintended leakage, etc. Things like that. And there's a breakdown by countries. Canada, the oil production, that's the grams of methane produced per barrel of crude oil. These numbers are here. Look how high Canada is. This is the tar sands and stuff. And there's a breakdown here. So, bad Canada. These are some of the scenarios for increases of anthropogenic emissions. If you mitigate, this is some of the modeling, but we're not seeing that happening in reality. And again, this is the sectors and different models. You know, some of the things that can be done to try to reduce the emissions. And here's baseline emissions modeled for 2030 based on all of these different things, based on, you know, where we're heading. You know, if you're heading somewhere, you get there eventually. This is the megagrams of methane emitted at a well per petajoules of oil or gas produced. Again, you can see this is oil production. Look at where Canada is versus the U.S. And this is gas production. U.S. is much higher. Russia's high. Canada's still got a big chunk here. Now, in terms of atmospheric monitoring, long-term methane monitoring, where does the methane come from? If you detect it by a satellite in a certain region, or if you have a base station, say alert, and you have your measurement equipment on methane, where is the methane coming from? And what are some of the ways, isotopic signatures of the methane that allow you to find out where it's coming from? So these are a whole bunch of stations for long-term monitoring sites. This is how long they've been working for. So, 1985, alert. This is alert in Canada, height above sea level. So this is Flask, hourly measurements, monthly measurements. Okay, and these are different sites. So you can see some are intermittent, some are coming online, others have been online and drop off, and so on. Okay, and this is some of the data, which I've shown you these three plots before. This is a time series of methane at different background sites, not smoothed out, and the slope or derivative here. Okay, you can look at the residuals, which is a change in methane between different, so you can take a zonal mean around the planet at 53 degrees, take what the mean at 90 degrees, take the difference, do it for CO, carbon monoxide, and do it for methane, and this is the type of thing that you can see. Okay, this is a difference between the northern polar regions and the southern polar regions. Okay, and this is quite interesting. Thanks.